AP Calculus, Unit 6, Integration and Accumulation of Change. We're going to study 6.1, Exploring Accumulation of Change today. And we're going to be talking about what the area under a curve is. In this unit, we're going to be going backwards. Integration is going from the derivative to the original function. So far, we've only been taking derivatives. And we would take the derivative and get the derivative of something and then use that equation to find tangent lines and that sort of thing. Now we're going to go backwards. We're going to be given the derivative and go backwards to find the original function. And you need to understand what the meaning of a derivative is. If we're exploring accumulation of change, basically the area under the curve is what you're talking about when you're talking about an integral. We're finding the area underneath the curve of f of x. Now, I've got three basic graphs here. And one thing you need to understand about when it says find the area under the curve, they're not actually talking about the area underneath the curve itself. If we were, the area under this curve, if I'm talking about going, and they'll give you a specific interval to go on. So I'm going to go from 0 to a for all of these. So I'm only going to be talking about y or x equals 0 to a in all of these functions. So if you think about the area under the curve for this one, well, wouldn't it be everything underneath this curve and it would always be infinity? Because if we're taking the area under a curve, well, unless we know what the bottom portion is, it's always going to be infinity. So that's not what they're talking about. If they refer to the area under the curve, what they're actually referring to is the area between the x-axis and the curve. So when they say find the area of the curve on the interval 0 to a for this one, the area under the curve is going to be the area between the curve and the x-axis. Here, the area under the curve is the area between the curve and the x-axis. So if you think about it, it's those three sections there. Now, one thing you need to understand is if that area is above the x-axis, it's considered positive. But if the area is below the x-axis, it's considered negative. So for this one, if we're finding the area under the curve, this portion up here would be positive, but these two portions down here would be negative. So we would take the area above and subtract from it the areas that are below. Here, this whole thing is going to be positive because it's all above the x-axis. In the next one over here, this one is completely below the x-axis. So if we're talking about the area under the curve, we're talking about the area between the curve and the x-axis. And since this portion is all underneath the x-axis, the whole thing would be negative. Now, you might be saying, well, you can't have a negative area. That's true, but all of these aren't going to be talking about area. Some of them are going to be talking about speed when we're referring to what they're asking us to find in the problem. So we can find the area and recognize that maybe this area represents a speed. And remember, we've talked about if speed is negative, it doesn't mean we're going backwards. It just means that we're going in a downward position. So if you drop like a ball off of a cliff, well, it's going to have a positive speed, but it's going to be represented as a negative when you're talking about the number because it's falling, it's not going up. If speed is positive, it's going in an upward direction. And so that's something that you need to understand. We can have pictures that appear to have a negative area, but we might not be talking about area at all. We might be talking about speed or velocity or just different types of problems that aren't necessarily geometric problems. We can represent them geometrically, but they don't represent a shape at all. Next, I want to talk to you about the calculus symbols for integration. The symbol for integration looks like this, and that means find the integral of a function. Now, if our function here, if this blue line is our f of x function, and I want you to find the area of the curve between x equals a and x equals b, the numbers that go here would be the lowest x value to the highest x value. So we want the integral from or on the interval a to b of the function f of x. That is the formula for find the area under the curve from a to b. Okay, so you need to understand how to set something like that up. And remember, part of it could be positive, part of it could be negative. You would just have to understand based on what the graph looks like, whether you're going to make it a positive or a negative. Above the x-axis positive, below the x-axis negative. I'm going to introduce area under the curve of a basic geometric shape using a problem that you're very familiar with. I'm going to show you how we can set this up geometrically with calculus with something that you already know how to do. So this says that you are on interstate driving at a constant speed of 70 miles per hour for 3 hours. How far have you traveled? Well, you learned a long time ago that if you multiply your speed times the number of hours, then you know your distance traveled, because distance equals rate times time, speed times number of hours. So for this problem, if you're just asked how far have you traveled, well, you would take the 70 miles per hour, your speed, multiply it by the number of hours that you've traveled, and understand that you have 210 miles. But sometimes they're going to give you a similar problem, and they're not going to give you all of this information, but they're going to give you the problem as a graph. So I want to show you how this can be related geometrically so that you can see how calculus is involved. If we were to set this up, what I'm going to do is I'm going to set it up as a graph. I'm going to make this, now there are two things that we've been given. We know we're traveling 70 miles per hour, so that's our speed, and we've gone for 3 hours. So I'm going to let this axis be my number of hours, and I'm going to let this axis be my speed. And if I think about that geometrically, we've been traveling, they said, for 3 hours, so that's going to be 3, at a speed of 70 miles per hour. So there's, I'll say that's 70. Okay, they're going up by tens. So if I've traveled at 70 miles per hour for 3 hours, I have this rectangle here. If you think about it, wouldn't the area of this rectangle be 3 times 70, which is 210 miles that we've traveled? Okay, so the area under this, it's not really a curve, it's a straight line, but the area under the curve that we're considering here is 210 miles. Okay, so you could set this problem up as a geometry problem and solve the area under the curve based on that rectangle. And we're going to start out, instead of starting out with curves, actual curves and f of x problems, we're going to start out with common geometric shapes that we've already learned in geometry and find the area under the curve using regular geometric shapes at this point, and then we'll move into the functions throughout the chapter. I know that 70 miles per hour times 3 hours means I've traveled 210 miles, but what if they give you a graph like this and you're trying to figure out what the unit of measure is, and you just can't figure it out? Well, here's what you would do. If you take speed, the unit of measure there was miles per hour, right? And this is the number of hours. So if we think about this, isn't miles per hour miles over hour, miles per hour, okay? And this is our number of hours. To get the unit of the area of measure, you would take this unit of measure, miles per hour, miles over hour, and multiply by this unit of measure, hours. Well, if you multiply those together, don't the hours cancel out? So your unit of measure here would be miles. So if they give you something like this is minutes, and this is gallons per minute, let's say we're filling up a pool or something like that, well then minutes times gallons per minute will be the number of gallons in your pool. So that's how you would figure out your unit of measure based on what your x and your y axis are. So the x value times the y value will give you your unit of measure of the inside area. So that's an easy way to figure out your unit of measure. And that unit of measure becomes important, especially when you're dealing with the AP calculus test, because they're going to want you to have correct units. You'll get all the points if you have the correct units. If you leave the units out, sometimes you might miss some points, and those those simple points like that you don't want to lose. So for the next segments, I'm going to show you some geometric shapes on the computer. We'll solve those on the computer screen to make sure you're understanding how to find the area under a curve. So for this segment, we're going to take some of these integral problems and find the area under the curve. And remember, we said that the area under the curve is going to be the area between the curve and the x-axis. Anything above the x-axis would be positive, anything below the x-axis would be considered negative. And in this problem, it says find the area under the curve for the graphed function for x is between -1 and 6. So if you look over here, the graphed function that they have here goes from -2 to 7. So we're only interested in the part that goes between -1 and 6, which would be right in here. So if you look at this right here, we've got the integral going from -1 to 6, so that's your a and your b. The integral going from -1 to 6 of f of x. And when I do this, I'm just going to be considering the part of the graph from -1 to 6. And these graphs are usually going to be composed of some simple geometric shapes that we learned how to find the area of in geometry. So I'm going to now take this and I'm going to separate each section into a different color, and then we're going to talk about the formula for the area of that and how to find the area underneath the curve. So I've got this shape that I'm trying to find the area of separated into 4 different sections. This blue section right here would be a rectangle above the x-axis. We know from geometry that the area of a rectangle is length times width. We know that the area of a trapezoid, the red section here, is 1/2 the height times base 1 plus base 2. And then each of these green sections are triangles, and hopefully you notice that those 2 green sections are triangles that are the same exact size. The length is 1, the width is 1, and the area of a triangle would be 1/2 base times height. So if we do 1/2 base times height, we would have 1/2 times 1 times 1, and here we would have 1/2 times 1 times 1. And this one is above the x-axis, so it's positive. This one is below the x-axis, so it will be negative. So these 2 will end up canceling each other out. So if I find the area of the blue section plus the area of the red section, and the green sections cancel each other out, the area of the blue plus the area of the red is going to be the area under the curve for this function. So for the rectangle, the length is 5. And the width is 1, so that means I would have area equals 5 times 1, or 5 for the blue section. And then if I consider the trapezoid, the area of a trapezoid is 1/2 times the height. The height here is 1, and then the bases are 3 and 1, so we've got a 3 plus 1. So 1/2 times 4 is going to give us 2. To get the final answer here, we would add 5 plus 2. So the area under the curve here would be, in this problem, it says the graph below represents the rate at which water is leaking out of a tank. The units are given in the graph. How much water has leaked out of the tank after 9 minutes? Okay, so time starts at 0 and goes to 9 minutes. So we are finding the area under the curve of this entire graph. Remember units of measure. We said in the other section at the whiteboard that your units of measure would be your x here, that measurement for x, times the measurement for y. Now the measurement for y is gallons per minute, and the measurement for x is minutes. And if we multiply those 2 together, gallons per minute times minutes over 1 would equal a unit of measure of gallons. So if we find the area under the curve, it would be whatever that area is, that number of gallons for our answer. So to separate this out, it looks to me like I've got a semicircle here. I've got a rectangle underneath there that goes all the way to 0. And then I've got a triangle here.
So I'm going to just separate this into the 3 different sections that I have. So there are 3 formulas that I need. The area of the rectangle. Area of a rectangle is area equals length times width. I need the area of a semicircle. The area of a circle is area equals pi squared, but since this is a semicircle, I'm going to divide that area by 2 because I need half of that area. And the area of a triangle is area equals 1/2 base times height. So I'm going to put the lengths in there based on what the graph is showing me and find my area under the curve. For the rectangle, this length is 6, the width is 2, so 6 times 2 would be 12. For the semicircle, I have pi, my radius is 2, so I have 2 squared, which is 4 pi, and that's divided by 2. So the area there would be 2 pi. Then my area for my triangle, the base is 3, the height is 2. So if I have area is 1/2 base times height, I would have 1/2 times 3 times 2, which would give me 3. Then to get my final answer, I would add these together. So 12 plus 2 pi plus 3. 12 plus 3 is 15, plus 2 pi would give us an answer of 15 plus 2 pi gallons for our final answer. In this one, the function f is shown below. What is the value from -6 to 9 of f of x dx? F of x dx is just another notation. The f of x represents as a function. Dx tells you that the function is a derivative of the original. That's what the dx means there. Another way we can refer to the dx is that that's the thickness of the individual rectangles being drawn, and we will talk about that in the next section. So don't worry too much about that notation at this point. We will learn more about it later. And it says write your answer in simplest form. So the next thing I'm going to do is I'm going to consider the different shapes within this. Now we're only considering from -6 to 9. We're not considering the entire function, just from -6 to 9. And then we need to find the area under the curve. So this rectangle, the length would be 4, so that's a length of 4. The height is 5, so the area underneath that portion of the curve is 20. This is a triangle. The base of that triangle is 4. The height of that triangle, again, is 5. So the area under the triangle, that is 1/2 base times height. So 1/2 of 4 times 5 would be 20 times 1/2, or 10. Here I have a small triangle. The base of that triangle is 2. The height of that triangle is 2. The area of a triangle is 1/2 base times height. So base times height would be 4. 1/2 times 4 would be a 2. And then the area of this rectangle, the base goes from 4 to 9. So the length would be 5. The height would be 2. And 5 times 2 is 10. So to get the area under the curve, we would add 20 plus 10 plus 2 plus 10. The area of this rectangle plus the area of this triangle plus the area of this triangle plus the area of this rectangle would be 42 square units.